Continuing our factor group computation ideas, let's look a little more closely at what happened with our computation for Z4 times Z6 mod the normal subgroup generated by 0, 2. The 0 there caused there to be no effect in this first factor. And really, all our division occurred between looking at what happened when I looked at Z6 and the coset of 0, 2. There's only one other coset. That means that group has to be of order 2, and that means I have Z4 by Z2. I collapsed the Z6 part from 6 things down to 2 things. And I didn't do anything at all to Z4. So what if I were to take this exact same group, use a different normal subgroup? Let's consider what happens if we do Z4 by Z6, but instead of going by 0, 2, we mod by the subgroup generated by 2, 3. Okay, before I actually do any computational work at all, let me waste my hands at this. If I was thinking of the subgroup generated by 2 within Z4, that should give me 2 things. 2 and 0. So I would expect the Z4 to collapse by 2. The subgroup generated by 3 in Z6 is just 0 and 3. I would expect that to collapse from 6 down to 3. So I should go from the group we originally had. I collapse this piece, I collapse that piece. I should get something of a much smaller order. I should get 3, and I should get a group of order 6. Collapse this from 4 to 2, collapse this from 6 to 3. 2 and 3 should give me 6. But my collapsing factors aren't independent of each other. Same damn word, same meaning. I'm not acting as like they're linearly independent here. They're connected. So let's look at the subgroup generated by 2, 3. How big is it?
Two, 3, and 0, 0.
That's exactly right. This has order 2. Hey, wait a minute. What's Z4 by Z6 have as an order? Which means if I do this, I shouldn't get something whose order is 6. 24 over 2, I should get something whose order is 12. So I didn't collapse them separately from one another. My actions weren't independent. They are connected viscerally. I get a much larger group than I originally expected. There's a problem here. I know this group is abelian. this is abelian and this is abelian. All of my actions here are abelian. How many possible groups of order 12 are there? Why?
Z12 and then Z3 times Z2 times Z2 and then Z3 times Z4.
Okay, but 3 and 4 are relatively prime to each other, right? So Z12 and Z3 times Z4 are actually isomorphic.
So there'd be two.
There are only two of them. It's either the product of 4 and 3, or Z2 by Z2 by Z3. And how am I going to figure out which it is? That's a good question. It's not automatically obvious which of these two it should be. But the only difference is in the 4 part, right? If I ignore the Z3s here, the top one is cyclic. The bottom one is the Klein 4 group. C2 times C2. That means this group has an element whose order is 4. It would go around the cycle Z4 and not change the Z3 part at all. Yes? The bottom group has only elements of order 2, 3, and 6. It has no element of order 4. Because the Klein 4 group only has elements of order 2. EA, EB, and EC are my subgroups of size 2. There is no subgroup no single element that generates the whole Klein 4. So, if I look at this collection of cosets and I find one of these cosets has order 4 in the arithmetic of cosets, then I know I'm in the top group. If I find that all of the cosets I look at only have order 2, then I'm in the bottom group. Or 2, 3, or 6, but none of them have order 4. So really my question now is, can I find element order 4? Now there are algebraic ways to do this. There are visual ways to do this. Go back and draw the lattice, like we did up here, with all the cosets in them. Now, in this case, I'm going to get 12 cosets, and they're not going to line up straight up and down. Where's my normal subgroup? The normal subgroup is these two elements. Now, here's the visual version of this. You see a way to walk this coset, make parallel copies of it, either up and down or left and right, and end up with 4 in a row. Sneaky part. We're working in Z4 and Z6. You go off the right edge, you come back on the left. You walk off the top, you come back up on the bottom. We're working in modular arithmetic. Technically, I shouldn't draw this picture flat. I should draw this picture on a donut, which connects the left side to the right side and the top side to the bottom side. I got all those donuts in the cafeteria. I should have saved some for this experiment. I could go down and get a bagel. We could Sharpie all over a bagel. I don't recommend it. I did it in graph theory once. It was very, very, very unpleasant. Give me an element that's not in the normal subgroup. An easy one.
1, 0.
1, 0. What's the coset? 1, 0 plus 2, 3.
Three, 3, and 1, 0.
Aha. Which is here. Excusing my crappy art. Hey, those are parallel, aren't they? I wonder if this coset has order 4. How do you determine if a coset has a particular order? How do you determine if an element has a particular order? You keep doing the operation to it. So I would add this coset to itself. And I would see if after 4 of those, got back here. So this is copy number 1. What happens if I add 1, 0 again?
Zero and then 4, 3.
I'm in Z4.
So 0, 3.
Here's the I went off the edge moment. This point and this point should be together. So I start coming up and then I end up there. So somehow I kind of wrap around.
So in theory, could you be going vertically as well and have the same thing happen? On the individual, I mean?
Yes, if I went off the top, I'd come back up the bottom.
Right.
Yes, absolutely. The problem is I'm looking for something of order 4. I'm not sure if I go off the top, I'll get something of order 4 or not. I don't know yet. Haven't done that direction. I'm working to the right at the moment. Okay, one more time. If I add 1, 0 to this thing, what do I get?
Zero, 1, 3.
And again, I see if I want to connect these 2 dots, 3, 0 and 1, 3, I go around. What happens when I add it again?
Go back where we started.
Which means that is our normal subgroup. That's this one, the red one. As opposed to these orange ones. That's this sucker. And if that's our normal subgroup, that plays the role of the identity in this group of cosets, which means I found a coset of order 4. Yes, sir.
I have a question. So in the top part, is that 2, 3 in the first word?
Here?
Yes.
Yes.
And why would we use that instead of 0, 0?
Because that's where I started the problem.
Yeah.
And now all of a sudden, tell me what happens when you start to go up. We didn't go up at all. We only went to the right. If I go up, I could get the dots that go from a height of 1 to a height of 4, or I could get the dots that go from a height of 2 to a height of 5. But then if I try and go up again, what happens?
to the bottom.
And I run into a group I've already hit, haven't I? So from left to right, I see something of order 4, and from top to bottom, I see something of order 3. And that tells me what group I'm in. I'm in Z4 by Z3, not Z2, Z2, Z3. I was able to discern the structure of the whole thing looking at this. I know, it's a visual argument, but that's why I did the algebraic version over there. I can find an element of order 4. One of those groups has it, the other one doesn't. I know which group I'm in. Questions? That's weird. The reason I use this lattice image is not because it's the easy one for me in general, it's because that's what the textbook uses. Let's consider for a moment a group of Betty number 2. Remember Betty numbers in our decomposition of cyclic groups? That was the number of copies of Z we had in there. What does this group look like? Well, it looks like ordered pairs, right? But ordered pairs, that's the Cartesian plane. It's only the integers in the Cartesian plane, which means instead of looking like a number line and a number line, it looks like a grid of dots. What is the normal subgroup generated by 1, 1? What's that made of?
Is that just ordered pairs of all positive numbers not including 0?
Unfortunately, no. That would have numbers that I can't get just from 1, 1. Because remember, the only thing I'm allowed to generate with is that element, right? So what happens?
So it's ordered pairs of the same number in each coordinate.
Right, so I get 2, 2, and 3, 3, and 4, 4, and 0, 0, and -1, -1, and negative, because it's a group, right? That's a line. That's the line y equals x. And all of the cosets then are parallel lines. There's 1, 1. And that's the subgroup generated by 1, 1 is the diagonal line y equals x. 125. But every coset means pick some number, some ordered pair, without the same numbers in it, and then add. And what you've basically done is change the y-intercept of your line, haven't you?
Why do they go into the negatives again?
Because every subgroup contains both the elements and their inverses. So all of my subgroups are generated this way. All of my cosets are parallel to that. And the only way to tell them apart is by their intercept. Every one of these cosets is of the equation y equals x plus b. And that tells them apart. We did this. We did this in Calc 1, where we talked about pictures of families of antiderivatives, the antiderivative of 3x squared is x cubed. No, it's x cubed plus c. What's c? I don't know. And then I showed you a picture of a bunch of parallel x cubed equations. Chapter 5, section 3-ish. We did this. We just didn't think of it in group theory terms. By the way, how many different options are there for a y-intercept? Since I can tell the cosets apart by their y-intercept, and there are infinitely many of those, this is isomorphic to z. All you have to do is tell me the y-intercept, and I know which coset you're in. And adding the two y-intercepts adds the two cosets. Now, what if I didn't use 1, 1? What if I used something else?
It'd be the same idea, just with a different slope.
That depends. Yes, I would get different slopes, but it depends on what number I use. What slope do you want to use, Reese? Okay, then I could go through 1, 5, right? That would give me a line of slope 5. Yes? And then all the cosets would have parallel lines with slope 5. Perfect. What's different here?
Instead of 1.
So what does that do?
Slow, but would not be allowed because it's technically a fraction, it's not an integer or an integer.
That's okay, I only care about the integer points on that line, right? So yeah, I would have 0, 0, and then I would have 2, 5. And there's no other integer point because it should technically go through like 2.5, right? So we miss the point at 1. There's no x value of 1 in this coset. I'm going to get more lines, aren't I? Because there'll be a line that goes through the 0 and 2 points. And then there'll be a line that goes through the 1s and 3s points, won't there? Which means if I move over 1, I get a parallel line, yes? But if I move up 1, weird things happen. I will still have infinitely many lines here. They'll just be spread out differently.
That slope be 5 halves? then?
Yes, absolutely. Would absolutely be a slope of 5 halves. I have no problem having a slope of 5 halves. I like that.
So then if you had, say, like 7 and 2, or 2 and 7, then the slope would be 7 halves?
And if I had 7 and 2, the slope would be 2/7. That's perfectly fine. That's absolutely correct. That doesn't help. What should I see here?
Slope of 2.
Great. But what's the normal subgroup generated by 2, 4?
Even answers.
Oh, it's not just the line of slope 2, it's only the even numbers on the slope of line 2. And that means I missed all the odd numbers on that line. That means on that line, technically, I'm going to have the normal subgroup and a coset. All of the even numbers are part of the normal subgroup. All of the odd numbers are a coset over. If you add 1, 0 or 0, 1 to that, you add 1, 1 to it, right? All of a sudden you're in a completely different place, which means each line contains 2 cosets. The even numbers and the odd numbers. So even though this line, it's kind of hard to see at the moment, let me put a break on it. This line, that's the line y equals 2x. That's the line with slope 2 going through the origin. The filled in dots are the even ones.
So the ones that aren't filled in, if they're not on the line, does that mean it's not exactly on that, or is it just how the picture is drawn?
It's just how the picture comes. Those are all on the same line. Like I said, crappy artwork. But so what happens here is I have a problem. Instead of just getting z, because I can tell all the lines apart by their y-intercept, I need to know whether I'm on the evens or the odds, which means this isn't isomorphic to just z. This is isomorphic to z times z2. Are you on the even ones, 0, or the odd ones, 1? So I have the z right here with all of the different y-intercepts, but then I have filled in versus not filled in, my z2 choice. When it comes to factor groups like this, I prefer to try and see what they look like. That's me. I can do this same calculation strictly algebraically by looking at the subgroup generated by 2, 4, that should be n in 2z, right? I need it to be even. So I get 2, 4, 4, 8, 6, 12. I don't get 1, 3. I get 0, 0. I get negative 2, negative 4. I don't get negative 1, negative 3. What do cosets look like? If I add a number in the y variable, my second coordinate, I don't change anything in x at all. I still have that same evenness in the first coordinate. But if I add 1 to the first coordinate without changing the second one, then I get an odd number and that is absolutely not the same as this. So I have cosets in 2 different directions. Like we looked at the Z4 going to the right, and we looked at the Z3 going up in our finite lattice picture. Here, even though my lattice is infinite, I can go up as far as I want. I can only go to the right 1 and end up on something different. Because if I go n plus 2, well, that's the same as being in here with a different value of n. The infinite ones are a lot harder. The finite ones are a lot easier. Doing this in 3 dimensions is mind-wrenchingly complicated looking. So Z2 by Z2 by Z3 would be a 3-dimensional grid of dots. I don't want to do that. I think it's actually easiest to do that on transparencies. You can actually see all the dots through all the layers. Works better on a computer, damn it. Questions?
Is it logical to say, like, if, like in the first example we did Z4, Z6, can we just rule out that it's not isomorphic to Z3, Z2, Z2 because it's only like the first group living in 2 dimensions?
Unfortunately, no. When I start with a product group, let's say I started with Z12, right? I could ask, is Z12, I know that's isomorphic to Z4, Z3. So even though the first one is 1-dimensional, the second one is 2-dimensional, but those ordered pairs behave the same way as those single numbers. Kind of a strange statement, but let me write it out. It might be easier. If I think of Z12 as the numbers from 0 to 11, and I think of Z, do you want to do 3, 4, or 4, 3? Okay, Z4 times Z3. Normally, I would just list all the rest of the ordered pairs, right?
Mhm.
Okay, I'm going to try and list them in a different order. Let's not do 1, 0. Let's do 1, 1. 1, 1 plus 1, 1 is 2, 2. 2, 2 plus 1, 1 is 3, 3. But there is no 3, 3. It's 3, 0. Add 1 again, what do you get? Add 1, 1 again, what do you get?
1, 2,
And again,
0,
and again,
1,
and again.
0, 2.
Keep going.
1, 0.
See why I didn't list it there?
Yeah. And then 2, 1. And then 3, 0. Yeah, 3, 2.
I just say I already ran into 3, 0. I can't run into it again.
And then 0, 0.
So I'm back around, right? So this is the subgroup generated by 1, 1. Which means this, in this order, is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 0. So it's two-dimensional, but it's really the same as the one dimension. So it's the way we write it. And this is the weird part. That's why I kept saying, while I make kind of a parallel to vectors, these aren't vectors. Kind of like two dials next to each other. And I have to operate on them at the same pace. And that's why being relatively prime allows me to use this as a generator. So unfortunately, that actually fails me, Reese. It would be a lovely dimensional analysis argument. I really wish I could do something like that. But you know, Z30, right? 30 is 2 times 3 times 5. So Z30 is one-dimensional, or it's three-dimensional. And now you know a deeper, much more important reason why I'm not a group theorist. Because I like thinking dimensionally, and that pisses me off. More questions? I went from 30 to 2 and 3 and 5, right? And those are prime factors. So would it be right to say Z2 and 3 and Z5 are somehow like prime groups? What's the definition of a prime number?
How many factors are one in itself?
And when we were factoring groups, we were looking for normal subgroups. So what if I looked at a group that didn't have any factor groups except for itself and 1? The identity. Okay, pardon my bluntness, what the fuck? What? The hell does this mean? What's non-trivial mean? For a group?
It's not just the identity.
Right. Trivial group contains one and only one element. Yeah. So G is not trivial. It's got other things in it. And has no proper mean. This is proper subgroup, proper, non-trivial, normal subgroup. So what's a proper subgroup?
Is it a subgroup that is contained purely within another group and not like possibly that group itself?
Yes. The improper subgroup is the whole thing. So a proper subgroup leaves out at least one thing. So proper, it's got to be smaller than the group itself. Non-trivial, it can't just be the identity. Normal subgroup. In other words, the only normal subgroups I can find are the whole group, which is trivially normal, and the identity, which is vacuously normal. A number was prime if it had no factors other than itself and 1. Every normal subgroup creates a factor group. A group is simple if it has no factor groups other than the group gotten from the whole thing or from the identity. And when I do G over G, G mod G, I get the identity. When I do G mod E, I get the whole group. So the only factor groups of G are 1 and itself, just like primes. Got no other factors. So in a sense, think of Z2. Z2 consists of the elements 0 and 1. The 0 is the identity. 1 is the whole group. So if I have both of them, that's simple. That's a prime factor. Z3, if you start with 0, you only get 0. If you start with 1, you get 1, 2, 0. That's the whole thing. You start with 2. Z3, 2 and 2 is 1. Add another 2, you get 0. You get the whole group. Z3 is simple. Z5 is simple. These are exactly my prime building blocks. But it turns out that there are lots and lots and lots and lots of very different simple groups. a very important result in abstract algebra. What's A5?
Even permutations of like 5.
Yes. It's the permutations of 5 elements, and it's all the even results. So the identity, and then anything made up of 2 transpositions, or 4 transpositions, or 6 transpositions. Okay. How many elements are in A5?
Zero, two, four.
Those are elements of Z5.
Okay.
But A5 is not even numbers in Z5, it's even permutations. Wait a minute, A5 is a subgroup of what group? Even permutations is a subgroup of regular permutations. So how big is S5? Aha. And A5 is half of that group. Somebody give me a number. Mm-hmm. Now here's a bizarre statement. 60 is a very, very composite number. 60 is divisible by 1, 2, 3, 4, 5, 6, 10, 12, 15, 20, 30. This is by a whole crap ton of stuff. Here's a group of order 60 with no factors other than 1 and 60. That's nuts. As much as I hate it, the book actually leaves the proof of this as an exercise, and that is bullshit. The proof is like this long. I don't want you to do it. I want to know why I care. Who gives up about the fact that this group is simple? It turns out that when you study polynomials, this is an algebra class, right? The purpose of algebra is to solve equations. We haven't done any solving of equations in this class so far. Why? Because I'm building the tools. I haven't even taught you what an equation is, much less how to solve it yet. When I look at polynomial equations, I can look at the roots. So I am going to write a polynomial of degree 5. If it's a degree 5, it has 5 roots. Now, some of them might be complex, some of them might be rational, some of them might be irrational, some of them might be whole numbers, some of them might suck. It doesn't matter. I am going to make sure that my polynomial has its leading coefficient of 1. So there's no ax to the 5th. It's just x to the 5th with a 1 in front of it. This is my polynomial. I factored it. Ta-da. In order for me to say, oh, I have I didn't use E on purpose. We use E for the identity, so I left it off. I have this equation, and I can get those 5 roots, root 1, 2, 3, 4, and 5, from the numbers A, B, C, D, and F. That would be a formula, like we do with the quadratic formula, right? And there's a formula for solving equations of degree 3. developed by Niccolo Tartaglia and Girolamo Cardano in the 1500s. There's a formula for solving polynomials of degree 4, developed by Fiore and Ferrari in the late 1600s, working off of Tartaglia and Cardano. I want a formula for these. If a formula exists that only uses adding, subtracting, multiplying, dividing, and the extraction of roots, taking square roots or cube roots or fourth roots, then that formula must remain the same when I permute the roots, when I use a permutation of the roots. But it turns out that that set of permutations must be even to keep the signs, the pluses and minuses, in the right place. So I need to use A5 on those roots. And for this to be invariant, I have to be able to find a normal subgroup for the invariance, for the inner automorphisms I sub G that we were looking at. If A5 is simple, then no such formula exists. Niels Heinrich Abel in the mid-1700s proved A5 was simple, and as such blew up the field of algebra completely and said, hey, all of the goals of solving equations by simple arithmetic ideas fail when we hit degree 5. There are no more easy methods. As a result of this problem, whole new fields, I use that term literally, we'll talk about that next week, had to be developed to figure out how to get nice formulaic solutions to higher degree polynomials when we put restrictions on A, B, C, D, and F. So if we say, oh, well, what if we only used integers? Nope, still doesn't work. What if we use numbers of a certain type? What type? What will work, what won't work? If there is one thing I want you to understand about this course, is that it shook the world completely and broke our faith in the fact that we knew how to do everything algorithmically. And it's Abel's fault, and it's A5. A group you've already seen and already know what it does. And the fact that that group is simple is a huge, huge change. Take that one, put it in your back pocket, keep it. We'll use it later. There are lots and lots and lots of very large groups that are simple. Some of them are called Lie groups, and they're related to symmetries in higher dimensional space, like 3D space. Some groups are created by looking at words. I'm going to give you two symbols. We did this once already. Here's A and B. When you do B twice, you get the identity. When you do A 4 times, you get the identity. So I could write that as a generating set with rules. Stuff like this, these are called restrictive groups or free groups. And it turns out that if my group is simple and abelian, it's going to be ZP for a prime. So these prime number ideas are exactly what I want for abelian groups. In the 60s, 1963, two people, the book says Thompson and Fate, I've never read the book, the paper, showed that every finite non-abelian simple group had even order. A5 is non-abelian, order is 60, that's even, it's simple. All finite non-abelian groups have even order. And so there came a big question. Can I categorize all of these groups? And can I write rules and constructions for them? Now, our non-abelian groups came from permutations. They also came from things like the dihedral group, right? The dihedral group was based off of symmetries of an object. I could do that in 3D also. I could look at the symmetries of a cube, pick up a cube, turn it around, put it back. How many different ways can you do that? Turns out for a cube, the answer is 24. And they all correspond to different rotations and mirrors, just like our square. When the classification of finite simple groups was worked on, and it's been worked on for the past 50, 60 years, there were some questions as to how big these even orders could get and whether or not they could be constructed. In the 1980s, a guy by the name of Grice and Aschbacher proved that there is a group whose order is million, billion, trillion, quadrillion, quintillion, sextillion, septillion, octillion, nonillion, decillion, unidecillion, duodecillion, triskidecillion, quadridecillion. I've run out of Latin at this point. Quintidecillion and hexadecillion. That is 9, 12, 15, 18, 21, 24, 27, 30, 3, 6, 9, 12, 15, 18, 8 times 10 to the 54th. This group has more elements than there are seconds in the universe since the Big Bang. The proof that this group is simple and finitely constructible and is a dihedral style group was put out in the late 80s. The shape that is the foundation for this group, instead of being like a triangle or a cube, the right shape to have this group is in over 120 dimensions. Seriously, dude, I don't hallucinate well enough for that. For the result, this is called the monster group. It's the largest finite simple group known.
Wait, why did they do that again?
I wish I could answer that question. Because it was there. They were trying to finish the proof that we knew what all finite simple groups looked like. And that final paper, by the way, was well over 5,000 pages. But they had these weird ass groups sitting out there like, well, is this one simple? If so, what is it? What kind of group is it? These are called sporadic groups. And the Lie groups are in that category, and these finite generated groups are some in that category. But the monster group was the last one in the 80s that they were really stuck.
Has that result led to other results since?
Oh, yeah, lots.
Okay.
The classification theorem gives me a lot of what comes out of, and we will see, in cryptography. I'd love to say it was useless and didn't go anywhere. It's in your pocket right now, protecting your credit card. It's keeping your password safe on your phone. Useless. We're never going to use this anymore. So, if we think about the group we were working with earlier, where we had to decide between 4, 3 and 2, 2, 3, 4, 3 is not simple. The group Z4 times Z3 has a normal subgroup of size 2 in it. But how would I know if G mod n is simple? How do I know if I've divided by a big enough thing to result in primes? Turns out that homomorphisms can help me about this. I've seen this result applied in general, but now I'm applying it to normal subgroups. A homomorphism preserves subgroups. But more than that, it preserves normality as well. In both directions. If I have a normal subgroup and I take the image, that's normal. If I have a normal subgroup in the range and I take its pre-image, that's normal. So to answer that question up there, when is G mod n simple, I need to think about dividing. If I want to make sure that I end up with a prime, I need to divide by everything else that's other factors, right? If you take a number, 150, and I want you to divide by something and result in a prime, you have to divide by as much as possible of the rest of the number. 150 is divisible by 3. If I do that, I get 50, which isn't prime. But if I go the other way, and I divide by 50, I do get a prime. So 50 is a big factor rather than a little factor. So let's look at subgroups that are as big as possible. A normal subgroup is maximal. Let's call it M. If it's proper and M is not a subgroup of N for any other normal subgroup of G. Also proper. Maximal, not maximum. I've made this distinction in other classes too. So if I think of Z6, the subgroup generated by 2 is 0, 2, 4. But there's no other subgroup in Z6 larger than that, other than the whole group. And since Z6 is abelian, that's a normal subgroup. Since there's no other normal subgroup above it, that's maximal normal. But wait, there's more. The subgroup generated by 3 is 0, 3. That's also maximal normal. Because there's no other normal subgroup above it in my subgroup diagram. As a matter of fact, the only other group left in the subgroup diagram is the trivial one. See how they're at the top of the chain, going from the bottom up? If we had a larger subgroup diagram, there might be more moving up and down. And it depends on what collection of subgroups we are looking at. If you go back to some of our other subgroup diagrams, you'll see this. If I have a maximal normal subgroup, then when I factor by it, the result is simple. In abelian groups, simple groups are prime. They're prime numbers, ZP. In non-abelian groups, they're harder to deal with. So it would be nice to try and make the most abelian part of a group. There are two special subgroups in a group that are made out of looking at abelian things. But I've done something stupid and run myself short up against the clock. The two subgroups are called the commutator and the center. And I think they're interesting subgroups, but they're far more useful in a direction we are not going to pursue. So I'm going to go ahead and send you all an email removing one of the questions from the homework assignment from this section. I'm not going to cover center and commutator. My goal, though, is now to try and figure out how to get to solving equations, and that means I need to bring back more than one operation. That means I have finished our study of groups. Gee, that means we should have an exam for the rest of this group stuff. Tuesday's the review day. The review sheet's on our attendance page. If you came in late and have homework for me, come give it to me. I'll see you on Tuesday.
Maybe next Thursday.
No, the following week. It would be Tuesday a week.